During today's lesson, we're going to be using something called the gradient-intercept form, or we're going to be delving into it. And we need to define a few terms. Last time we talked about the gradient being m, but now we need to know about the y-intercept, which we use the letter c for. Not really sure. In some other countries they use b or a completely different letter. So the y-intercept of a line, which we're using c to represent, is where the line crosses the y-axis. And we've looked at some intercepts before, but it's new to us to be calling it c. When written as a point, y-intercepts always have an x-coordinate of 0, and we've talked about that a couple of times. So it says, list the y-intercepts for the following lines, also write as a coordinate. So the y-intercept is where it crosses the y-axis here. So here, the y-intercept is 2. We could now write that as c equals 2, c being the y-intercept. Now if we were to write that as a point, that would be x would be 0 here, and y would be 2. Because as we said, y-intercepts always have an x-coordinate of 0. Okay, next example. Here's our y-intercept. So we could write y-int being -1, or now we could just write c equals -1. And as a point, that would be x is 0, y is -1. So let's put it all together. We've spoken about a lot of these quantities separately. Let's really amalgamate them. When we previously determined the rule from a table, we said that linear graphs are usually written in the form of y equals mx plus c. And as we said, m is the gradient, and c is the y-intercept. I'll just write y-int. Now we previously did finding the rule from tables, so let's do a nice bit of revision for that. We said that y equals mx plus c, and we said that m could be found by the change in y over the change in x. And we previously said c was the value that we needed to add on, or it was the y-intercept. So recall, we had to find out what x was going up or down by each time. So in this case, it's going up by 1, and that was equal to the change in x. That triangle is the Greek letter delta that represents change in. Now we need to look at what y is doing each time. Well, it's actually going down by 2. So -2 is the change in y. So the gradient was equal to the change in y over the change in x. Change in y was -2, change in x was 1, so the gradient is just -2. And to find c, which we said was the y-intercept, we had to find the point where x was equal to 0. So that means c equals 2 here. So let's note that down, c equals 2. So the rule, y equals mx plus c, could be written as y equals, instead of m, we're going to put -2x, and plus 2 on the end. That is the rule for the line that we've come up with here. Now, let's actually do finding equation from a graph now. So we did finding the gradient during our last lesson. Let's implement that again here. So you might draw a slightly different triangle, but I'm going to draw this one. I notice that these jumps are 2 each time. So if we have 2 jumps on the side here, that means the rise here is actually 4. The run, well, I notice this is 2 units wide, so the run is going to be 2. Not -2, we just care about the length, which is a positive value. The negative comes into place when we have that remaining side, so we put the negative there. So m equals plus or minus rise over run. So that's negative, the rise is 4, and the run is 2. So that simplifies down to -2. Now the y-intercept is where it crosses this axis, so c would be equal to 2 here. So c equals 2. So the rule, y equals mx plus c, it's going to be y equals -2 for mx plus 2 for c. Now did you notice something? These two rules are the same. So that's interesting. It's telling us something about this table and this graph. Firstly, you might actually notice that all of the values in the table have been plotted on the plane below. And what you might also notice, a deeper layer here, y equals delta y over delta x, or change in y over change in x, has a lot to do with the gradient formula, rise over run, because rise is in the vertical direction, having to do with y, and run is in the horizontal direction, having to do with x. This also has a lot to do with the other equation that we had. Remember when we did m equals y2 minus y1 over x2 minus x1. That's the same as saying the change in y over the change in x. You're finding out how much y goes up or down by from one point to another, and how much x goes up or down by one point to another. So, although we've been learning this in different contexts, all of these are related. All of these are talking about the same thing. So what do we notice? These graphs are the same. So these graphs, so the one in table and one plotted, have the same rule, therefore are the same. They're just two different representations of this information, which is pretty cool. So we now want to determine the equation of the following graphs. To be able to do that, we need to know that y equals mx plus c. So in each instance, we're going to find out what m and what c is. C could be a positive or a negative value, same as m, positive or negative, and we'll write that as our rule. So with this graph here, checking our axes, this has a run 1, rise 2, and it's a negative line. So that means m is going to be plus or minus rise over run. So rise of 2, run of 1, and it's negative. So m is negative 2. C is going through 3 here. So that means the rule, or the equation, could have been written as equation or rule, always looks like this. Y equals mx plus c for the majority of our lines. So that means y equals mx plus c, y equals m was minus 2x, and then we've got m was minus 2, we put that x on, and then we add 3 for c. Okay, another one here. This has a rise of 2 units, a run of 3, and it's positive. And I notice c is negative 1 here. So m equals plus or minus rise over run. It's positive, the rise is 2, and the run is 3. And we said c was equal to minus 1. So y equals mx plus c gives us y equals 2 over 3x minus 1. I could have written plus minus 1, but we don't want to have a plus and a minus in our final line of working out. Oh, this one's a little bit trickier. We need to be careful to find a point that's actually on the line. So I think my ruler will help me out here. So if I'm looking here, this point, oh, have I done that correctly? Let's try and draw it. From there to there, then we need to draw downwards. Is that going through that too? Oh, I'm not convinced whether it is. Ah, there we go. I'm pretty convinced with that now. So that means we can make this triangle above or below the line, doesn't matter. We've got a rise of 1 here. We've got a run of 2, and it's a positive line. So the gradient, let's pop in the formula like we always do. Remember that plus or minus is just a prompt. Is it an uphill or a downhill line? So that's positive, rise of 1, run of 2. And c, in this example, it's going through the origin, so c is going to be equal to 0. So y equals mx plus c means y is going to equal a half x. And we don't even need to put in the plus 0. So here it is. This is the rule or the equation for each of these graphs. And these are our final answers, because all it asks us is to find the rule or the equation. Ooh. So last little bit of this example, I've written over it a little bit, but I'm sure you can manage. We want to extract the gradient m and the intercept c. So remember, the gradient m is whatever is attached to x, and the intercept c is whatever is hanging out, added or subtracted on the end. So in this example, the gradient is 2, because that is what is actually attached to our value of x. And c is what is added or subtracted, so it's positive 5. We can just write 5. Let's do that for the next one. Gradient has to be the thing attached to the x, which is 3, and the y-intercept is the number added or subtracted, so it's minus 4. In this example here, we've got an invisible 1 in front of our x, and the y-intercept has got to be negative 6. Gradient for the next one, negative 2. Notice with none of our gradient values, we're not writing the x. We just know that the thing attached to the x is going to be the gradient. Y-intercept is 3. Gradient for the next one is 5, and because we have nothing added or subtracted on the end, we can actually say the y-intercept is 0. Oh, now the next one's interesting. We've just got y equals 9. There's no x here. We could imagine that to have a plus 0x, because 0 times x would give us 0. So that means the gradient is 0, and the y-intercept has got to be 9. Next one's trying to trick us a little bit. We've got an invisible 1 in front of that x, but it's not just an invisible 1, it's an invisible negative 1, because it also includes that sign. So the gradient would be minus 1, and the y-intercept would be 4. Okay, next one. This 3/4 is attached to the x, so we're going to have a gradient of 3 over 4, and the y-intercept will be 7. Now the next one is a little trickier. You might think, haha, there is an invisible negative 1 in front of that x. That is true, but this over 2 is also attached to that x. So the gradient here is actually a half. X over 2 could also be written as a half x. They both mean the same thing. Dividing x by 2 is the same as multiplying x by a half. And the y-intercept is negative 1. Okay, they tried to trick us with the next one. They'd flipped the equation around a little bit, but we still know whatever is attached to the x, including its sign, is the gradient, so it's negative 2, and the y-intercept is negative 3. Here's another one of those weird examples. X isn't just attached to the 5, it's also got this over 2. So it's 5 over 2 and minus 8 over 9 for the gradient. In these last examples, we're actually asked to write the equation. So this could be y equals 3x plus 2. If you wanted to be creative, you could also write that as y equals 2 plus 3x. Okay, the next one, y equals minus x minus 5, or if you wanted to be creative, y equals minus 5 minus x. Next one, y equals minus 3x. I could write plus 0, but I don't need to. Next one, y equals minus 2 over 7x minus 4, or if you wanted to be creative, y equals minus 2x over 7 minus 4. And the last one, y equals a third x plus a quarter, or we could do y equals x over 3 plus 1 over 4. To be honest, I really do prefer writing them the way that we've got here. I've just done the ones on the right because it is important for us to be able to notice it written in a slightly different way. Okay, we've got some families of graphs here. I noticed that we've got all of these graphs on the left-hand side are parallel, and I've called them a parallel family. They all have the same gradient. So same m. And what would that m be? Let's pick a line. Here to here. It has a rise of 2, run of 4, and it's positive. So all of these happen to have a gradient of positive a half, or just 1 over 2, because that's 2 over 4 simplified. Now in this set of graphs over here, they all have the same y-intercept. Same c. So they all have a y-intercept of 2. So we can have lines can have different things in common. Perhaps they have the same gradient, or maybe they have the same y-intercept. Now, what we've been building towards, we want to sketch graphs using the y-intercept and the gradient. So we can use that y-intercept and m to draw a graph. So here are our steps to success. Number 1, we want to draw a point at the y-intercept, and that's our c value on our set of axes. Number 2, we're going to use the gradient is plus or minus rise over run. And what we're going to do is we're going to rise up and we're going to run across, either positively or negatively in the x direction. And that will give us a second point. Once we've done that, we'll connect our 2 points and we've got a line. So that might seem a little bit strange at the moment. I promise you when we've done a few examples, it will start to make sense. Now a little point to note, if we had a gradient is a whole number, just say we had m equals 4, we need to know the rise and the run. So we are going to write any positive gradients, any whole number gradients over 1. So write, oops, I can't write all of a sudden. Write whole number gradients 1. So we can write any whole number over 1. So I'll show you what that looks like. We're going to sketch some graphs here. Oh, we've only been given 2 sets of axes, so we do need to carefully label some graphs. So first one, we've got y equals x, and that could be written as y equals 1x, and we could put plus 0, meaning our gradient is 1, and our y-intercept is 0. Now if our gradient is 1, we need to write that as a fraction, and because that's a whole number, we can write that as 1 over 1. That might look a bit strange at the moment. You might be thinking, why on earth are we doing that? Keep watching and you'll see. So, our first step to success, we need to draw a point at the y-intercept on our axes. So the y-intercept for this one was 0, so let's get our pencil ready to go. Now what we're going to use is we're going to use this to tell us how far we're going to rise. So we're going to rise up by 1. And we're going to use this number underneath, that's why we needed it, to tell us how far to run. So this tells us that we need to rise up 1. So I like to imagine I'm jumping up 1. Now I need to run, and I need to run 1 unit, and we're going to run to the right. So we have a positive line here. So let's get rid of my jumpy marks. Here are our 2 points. Remember, we only need 2 points to be able to draw a line, really. So, our ruler ready to go. Let's draw our line. Line it up as best we can. That's looking okay. And let's label it y equaled x, just because we're going to use this Cartesian plane for more than 1 point. More than 1 line, I should say. Okay, the next one. So automatically we see that c is minus 3. So perhaps I'll put that on my graph ready to go. Remember I'm negative, so I'm down here. Now my gradient m equals 1 over 4, and that's positive. So this tells us we're going to rise up by 1, and we're going to run by 4. So let's do that. We're going to rise up by 1. Pencil ready to go. Rise up 1. Then we're going to travel 4 places to the right. 1, 2, 3, 4. And that is our second point here. And if you weren't sure, let's draw that line. And then I'll show you what we can think of. So here's our line, nice and long, drawn in pencil. Y equals 1 over 4x minus 3. If you weren't sure, you could draw yourself a little triangle here that has a rise of 1, a run of 4, and it's positive. And it goes through the y-axis at negative 3. So the rule of that line has to be 1 over 4x, that's rise over run, 1 over 4, and negative 3. So that's a nice way to check afterwards. You don't need to do that, but you might find that reassures you about your answer. Okay, next 2 to do. Firstly, we can look at this first one here and say, c has got to be equal to 3. So let's be organised, use our pencil to plot that there. Now the gradient of this line, m equals negative 2 over 3. So that tells me we're going to rise up by 2, and this time, because we've got that negative, we're going to run to the left. Now there's different ways you can do this, but this is a way I find useful to talk about. So let's do that. We're going to rise up by 2. 1, 2. And now we're going to run 3 places to the left. 1, 2, 3. If you draw that line, you see we have, by running to the left, let's line it up, there we go. By running to the left, we have created a negative gradient or a downhill line as we required. If we'd run instead to the right, we would have had a positive line, and that would not have been what we wanted. So we'll label that now. Y equals negative 2 over 3x plus 3. Okay, the last one we're looking at. Firstly, I jumped the gun a little bit there. I know that c equals minus 5. So I've already drawn that on my graph. I got a bit ahead of myself there. Now we know that m is going to be negative 3 over 2. So that tells us the rise, I'm going to rise up by 3. And this time we're going to run, because it's negative, we're going to run to the left 2 places. So we're going to rise up by 3. 1, 2, 3. And we're going to run 2 to the left. 1, 2. You don't need to leave those jumpy lines if you don't want. So you can see running to the left here has allowed us to draw a downhill line. And let's label it y equals minus 3 over 2x minus 5. Very nice.